The natural world is a marvel of complexity, yet even the most intricate ecosystems pale in comparison to the technological revolution unfolding before our eyes. We stand at the precipice of the singularity, a point where artificial intelligence surpasses human intellect, forever altering the course of our species. This transformation, however, goes far beyond mere computational power. It delves into the very essence of what it means to be human. At the heart of this revolution lies nanotechnology, a realm of science that manipulates matter at the atomic level, blurring the lines between biology and technology in ways once confined to science fiction. This is not just a story of progress, but one of profound change. A change that prompts us to question our place in the universe and the very nature of our existence. As we delve deeper into this world of microscopic machinery, we uncover a future where the boundaries between mind and machine, reality and simulation become increasingly blurred. This is the future of the singularity, a future where the impossible becomes possible. The Defense Advanced Research Projects Agency, or DARPA, stands at the forefront of this technological frontier. Their research into brain-computer interfaces utilizing magnetic nanoparticles is a testament to the potential of nanotechnology to bridge the gap between the human mind and the digital realm. Imagine a world where thoughts are no longer confined to the skull, but can be transmitted wirelessly, where memories can be downloaded and shared. This is the promise and perhaps the peril of DARPA's research. By injecting microscopic magnets into the bloodstream, scientists aim to establish a two-way communication channel with the brain. These nanoparticles, guided by external magnetic fields, can then stimulate specific neurons, enabling the control of thoughts, emotions, and even actions. The implications of such technology are staggering. Coupled with advancements in fields like the High-Frequency Active Auroral Research Program, or HAARP, and extremely low-frequency, or LF, waves, the potential for wireless mind control becomes a chilling possibility. HAARP, originally designed to study the Earth's ionosphere, has been the subject of much speculation, with some suggesting it could be used to manipulate weather patterns or even control human behavior. ELF waves, meanwhile, occupy a unique niche in the electromagnetic spectrum, capable of penetrating water and even solid rock, making them ideal for long-range communication, including potentially communication with the human brain. While the scientific community remains divided on the feasibility of such applications, the very possibility raises profound ethical questions about free will and the potential for misuse. The FDA's approval of magnetoelectric nanoparticles, or MNPs, for use in medical imaging marks a significant step towards the integration of nanotechnology into human biology. These nanoparticles, with their ability to interact with both electric and magnetic fields, offer unprecedented control over neuron activity. By manipulating the spin rate of electrons within these particles, scientists can influence the delicate electrochemical dance that governs our thoughts and perceptions. While the initial applications of MNPs focus on treating neurological disorders, their potential applications extend far beyond the realm of medicine. The ability to directly influence neuron activity opens up a Pandora's box of possibilities, from enhancing cognitive function and memory to potentially altering mood and personality. To fully grasp the implications of this technological revolution, we must delve into the realm of quantum mechanics. Emerging theories suggest that the brain itself operates as a quantum computer, with microtubules, the structural components of cells, playing a crucial role. These microtubules, it is believed, store DNA not just as a blueprint for life, but as a repository of information, perhaps even containing memories passed down through generations, echoing the experiences of our ancestors. Some even speculate that this DNA could contain remnants of galactic memories, echoes of cosmic events imprinted on our very being, connecting us to the universe in ways we are only beginning to understand. This concept challenges our very understanding of consciousness and the nature of reality, suggesting that we are more than just individuals, but rather nodes in a vast cosmic network. This interconnectedness takes on a whole new meaning when we consider the concept of the cybernetic hive mind. With the ability to connect minds through technology, imagine a future where individual consciousnesses merge into a collective entity. A superintelligence capable of processing information and solving problems on a scale unimaginable to the individual human mind. This hive mind, however, raises profound questions about individuality and free will. In a world where thoughts and experiences are shared, what happens to the concept of the self? Do we become mere drones, subservient to the will of the collective? Or does this interconnectedness usher in a new era of understanding and empathy? At the forefront of this technological revolution lies graphene, a material with almost mythical properties. Composed of a single layer of carbon atoms arranged in a hexagonal lattice, graphene is stronger than steel, more conductive than copper, and incredibly flexible. These properties make it an ideal material for creating artificial neural networks that mimic the intricate web of connections in the human brain. Graphene carbon nanotubes in particular hold immense promise. Their ability to conduct electricity with virtually no resistance makes them ideal for creating the complex circuits necessary for artificial intelligence. These nanotubes can be arranged in three-dimensional structures that mimic the layered architecture of the human cortex, potentially paving the way for artificial brains that rival or even surpass our own. Scientists are already making strides in this direction, using a combination of hydrogel and graphene oxide tubes to create artificial neural networks capable of learning and adapting. Hydrogel, a biocompatible material with a remarkable ability to retain water, provides the perfect scaffolding for these networks, while graphene oxide tubes act as the conductive pathways, mimicking the function of neurons and synapses. These artificial brains, while still in their infancy, represent a paradigm shift in our understanding of consciousness. If we can create consciousness in a lab, what does that say about the nature of our own minds? Are we simply biological machines, albeit incredibly complex ones? Or is there something more, something that cannot be replicated in a laboratory setting? This question takes on a whole new dimension when we consider the concept of uploading consciousness to a cloud, a vast, interconnected network of quantum computers. Quantum time crystals, theoretical structures that exist in a perpetual state of flux, could potentially provide the key to achieving this digital immortality. By encoding our memories, experiences, and even our very sense of self onto these quantum structures, we could potentially achieve a form of digital immortality, our consciousnesses existing outside the confines of our physical bodies. This concept, while still firmly in the realm of science fiction, highlights the profound implications of the singularity, a future where the boundaries between life and death, reality and simulation, become increasingly blurred.